Yeah.
Okay. So the last talk before the break, for the session, is by Claudio Gorodski from the University of Sao Paulo, and he'll speak on the diameter gap for isometric quotients of the unit sphere. Thank you, Claudio.
Thanks a lot, Ramiro. Thanks also to Caroline and Romina for this nice opportunity to talk to you virtually. And right, I'm going to report on joint work with Christian Lange, Alexander Lytchak, and Ricardo Mendes. So what we, here. We're going to consider isometric quotients of the unit sphere. So as n of radius 1, so that is orbit spaces where G is any subgroup of the isometric group, right? And, oh, yeah. So of course, this orbit space carries a natural metric space structure, just given by the distance between the orbits. This is, of course, realized by geodesic horizontal geodesic orthogonal to the orbits at the endpoints. And there is a question, old question. So how small can X be, right? So there are maybe 1 or 2 papers by Carsten Grove and Mark Vorsen in the 1990s discussing metric invariants of, well, metric spaces and discussing this range problem, for instance. And so you can somehow fit this question there. And so what we show is that, of course, the diameter can be 0 if the group is transitive or if it has a dense orbit. But otherwise, there's a gap. So there exists epsilon, positive epsilon, such that for every n, at least 2, and every isometric action of G on the unit sphere, the orbit space has diameter either 0 or bigger than epsilon. So there's a gap there, right? So you cannot have arbitrarily small diameter, which is not 0. And so this is going to appear in the Journal of the European Mathematical Society. And right, of course, yeah, this remark, so diameter is 0 if and only if some G orbit is dense, which is equivalent to the closure of the group to be transitive on the unit sphere, and equivalent to the closure have orbit space of diameter 0 too. And of course, we need to start in dimension 2 because you have cyclic groups of isometries of the circle, and these, of course, are simple examples with diameter going to 0, right? Okay, so what about related work, preliminary, previous results, right? So there are a few previous results. So Sarah Greenwald, in 2000, she proved that for every n, there exists epsilon depending on n. And this is not explicit, and such that the diameter of X is bounded below by this epsilon, if it's not a point, right? And also, it was known, in some special cases, it was known that you could take epsilon independent of n. For instance, if the dimension of the orbit space is 1 or 2, right? The case of reactions where the orbit space is manifold or Coxeter groups, then you have the orbit space is an orbifold, right? So This was already known. So just to remind you, I mean, the case dimension of x is equal to 1 is the case of homogeneity 1 actions on the unit sphere. And in this case, of course, you get an isoparametric foliation. Right? If you take a normal geodesic to the orbits, then you get some focal points like that, and this parameterizes the orbit space. It's like an interval of length pi over g, where g is 1, 2, 3, 4, 6, right? And so in this case, the diameter, okay, this is for connected groups. If G is connected, right, then you get this picture. So at least 6, right? And if G is disconnected, then you can flip the endpoints by some element, and then you get this lower bound, pi over 12. So that's the situation for dimension 1, right? Okay. It's not working. Yeah. Okay. Now there is recent work, Gautier and Rossi recently, their paper is already published. They independently, they show the existence of a lower bound independent of n, but they only considered complex representations of connected Lie groups. So this would be like unitary representations. And they could not deal with the case of spin representations, because they did some, well, they reduced to some case-by-case analysis, and the spin representations were left out. But this is only for complex representation of connected groups. And there's another paper, more recent even, Ben Green, using different techniques, he proved a very strong version of our main theorem, but only for finite groups. And he showed that this epsilon of n goes to pi over 2 as n goes to infinity. But he only considered finite groups, and his proof is different from ours. Okay. Let's see. Now, yeah, this is a slide just to remind you. This is the classification of closed subgroups of the O3, right? So the case of S2. So we have the polyhedral groups here, right? So we have very explicit the diameter in these cases. Yeah, I'd like to remark that if you have a fixed point, then of course, antipodal point will also be fixed, and then this go to the quotient. So you have distance pi in the quotient. So that's why if you have a fixed point, you always get diameter pi, right? Which is the maximum possible anyway. And if you have a reducible action, so if you write a representation as a sum of invariant subspace like that, then each subspace will project to a different subsphere, and the distance here is pi over 2, right? So you get pi over 2 also here, right? You have the situation. Otherwise, it is less than pi over 2. the irreducible case. So this is, yeah, this is known. And
Claudio,
yeah,
can I ask you a question? So
sure.
the extension of Ben Green's result doesn't hold for arbitrary groups, right?
No,
That's what,
specifically he worked with finite groups, yes.
and you are showing some non-finite groups that for infinitely many dimensions, the diameter is less than pi/2, right? Is it correct? I mean, this tetrahedral and octahedral.
No. This is only case of S2, right? I mean,
okay.
Yeah.
That's one of my question. Thank you very much.
Yeah, this is just, you know, just to fix ideas, to have some context, right? But this is just preliminary, well-known results. Yeah, just S2. Now this, yeah, I'm going to start now to talk about our theorem, okay? I'm going, well, yeah. Now I'm going to discuss, to try to give some rough idea of our result and the proof, and okay. So let's assume the diameter is bigger than 0. We want to find this epsilon. It will be not explicit, okay? So of course we can always enlarge the group. This will only decrease the diameter. It's enough. So we can take we can take the closure. Then now we have a compact group, okay? Not necessarily connected, but compact. It will not be transitive in a sphere. So this is a folklore lemma that I talked to you. Diameter is pi if and only if it has a fixed point. It's pi/2 if it has no fixed points, but the action is reducible. And then it's less than pi/2 if it's irreducible, okay? This is not hard, this is a folklore result. So first step, we refine this result to show the following. So if we have a normal subgroup N of G acting reducibly, then it's really what we call super reducible. I mean, it will act like, you know, for instance, the complex case, like U1 acting on the connected component will be like this complex multiplication, and then you have some finite group also permuting this, right? So yeah, right. Or the diameter is big, is bigger than pi/4, right? So if the diameter is not big, then it's either irreducible or super reducible, okay? Yeah. Yeah, okay. So I just copy the same lemma here. So let's go to our proof. So assume G is compact and irreducible, okay? Otherwise the diameter is big. And then we apply this lemma to the identity component of G. Of course, it's a normal subgroup. So either the identity component will be irreducible or it will act as scalars. That is, G is a finite group up to scalars, okay? So G is a finite group, so either G is finite or it looks like what I wrote, something like that, some finite group cross U1 or SP1, something like that, okay? Or it will be irreducible. So these are the two main cases. So the first case, a finite group up to scalars, is the case that Ben Green studied. And right, and then the other case, G0 is of positive dimension and X irreducibly. So our proof is divided into these two cases. So in both cases, the bulk of our treatment is group theoretic, but we also use some Riemannian geometric arguments in an essential way. So I'd like to explain that. So let's first talk about the case G is finite up to scalars. Okay, yeah, the presence of scalars forces us to work with projective representations, but I'm going to ignore that. So let's consider the special case G is just a finite group, so we don't need projective representations. So assume G is finite. We can assume it's a maximal subgroup of the orthogonal group. In particular, the representation is of real type. So this is very simple. We just compare the diameter and the volume of the orbit space. This is very simple, okay? So of course, G is effective. So in this case, a finite group, and the volume of the orbit space is just the volume of the sphere divided by the cardinality of the group. On the other hand, the volume, well, the diameter is finite, so we can take a ball, is the volume of a ball, and then we can do some volume comparison here because X is positively curved. So we compare with the volume of the unit ball in Euclidean space, okay? Radius 1, so we get this, Bishop-Gromov. And of course, this is less than the, can replace the volume of unit ball is less than the volume of the sphere of the same dimension. This is simple too, right? Because, yeah, we have orthogonal projection here, right? And then we just put these two together, we get that the diameter is bounded below by, this is, yeah, this number 1 over order of G to the 1 over n, yeah. So it suffices now to find the universal lower bound for this number, log of the order of G divided by n, where n plus 1 is the dimension of the representation space, right? So what we have to show is that as the order of the group grows, the faithful representation of smallest dimension grow fast enough too, right? And so, yeah, we need to find another, yeah, what we did. Stupid thing here. Yeah. Yeah, in fact, it's an upper bound, right? Because you rewrite this. Yeah, it's wrong here. It's an upper bound that we have. So as the order of the group grows, the dimensional of the smallest dimension of a faithful representation must grow fast enough to have this bounded, right? And so if G is simple, the classification of such groups combined with the knowledge of the smallest dimension of faithful representation provides us with the desired bound. So here is where we use the classification of finite simple groups. And so the cyclic groups are the abelian case, right? And then we have alternating groups, Lie-type. Sporadic groups we don't need to consider because there are only finite many of them. So we don't care, right? And if G is not simple, then I don't have time. We have some tricks to reduce to the simple case. So it takes a minimal normal subgroup. it will be a power of a simple group, and then we can also deal with the quotient. But yeah, so there are some group theoretic tricks to deal with this case. So I'm going to skip that. And this essentially finishes the first part. Now let me talk about the second case where the identity component of G acts irreducibly. So first, we reduce the case G is compact, connected, and simple up to scalars. Because if G is a product, like semi-simple, for instance, the representation, irreducible representation, will be a tensor product, and this case is easy. Okay, so we can quickly reduce to the case of simple groups up to scalars. And then there's a paper myself with a student, in fact, where we considered representations of Lie groups, of compact Lie groups, which are not, connected in this case, which are not transitive on the unit sphere, and then we could show that we can always find a point such that the focal radius of the orbit through this point is bounded below by a universal constant. So this is a local result, right? Focal radius of one orbit. So this point will be a highest weight vector in case of complex representations, for instance. So let me remind you, what is the focal radius, right? So, well, focal point is where normal geodesics meet infinitesimally, right? So, right, so we don't have focal points here, yeah. Less than this distance, right, to this orbit. And so the focal radius is bounded below by this number. And there's another number which is important, is the normal injectivity radius of the orbits. So it's the radius of a maximal tubular neighborhood. It means that we consider the normal exponential map, and this maximal tubular neighborhood is the image of neighborhood of the zero section where the exponential map is a diffeomorphism, right? So I take a radius of a neighborhood of the zero section of the normal bundle of constant radius, right? And then exponentiate that. So that's the injectivity radius, where the exponential map is a diffeomorphism. And these numbers compare like that because a normal geodesic cannot be minimizing past a focal point, right? And right. Now there's an argument to get another estimate like that. So maybe I have time to explain this. So yeah, these numbers could be equal, right? But if they are not equal, in this case, if the focal radius is strictly bigger, so here's the tubular neighborhood, right? It means that focal point means that you have very, very close by geodesics meeting infinitesimally, right? Something like that, a focal point. But here, if the focal radius is bigger than the injectivity radius, means that you have two geodesics far away one from the other, which meet here, right? And then first we have to argue that they must meet smoothly here, because otherwise we can use the formula of first variation and construct a variation like that and construct two geodesics meeting closer to the orbit, and then this is a contradiction to, yeah, we'll get, this is a contradiction to this number being the injectivity radius, right? So they must, that it means that they must meet smoothly here. And this is a Riemannian geometric argument, right? But now we have to use some group theoretical arguments.
So this will be the closed geodesic in the standard Klingenberg estimate,
exactly,
right?
Yeah. The standard one, it goes back to the point here, we have an orbit, right? And so it's moved here, and then you need to use some particular thing about our point and some group theoretic representations. We can show, this is the point P, right? We can show that we can find a one parameter group, the isotropy group of P, which moves this geodesic. So we produce a variation of this geodesic, and this implies that P is a focal point of N. P itself is a focal point, but then the length of this geodesic is twice, right? So therefore we twice injectivity radius. Yeah, because we have two segments here, right, of the same length. Yeah. So we get this estimate. Yeah. So this is a Riemannian geometric argument, really very classical, but, and then we have to finish with some group theoretical arguments here. And okay, so, and then this finishes this case too, because by the other paper we have this estimate, we prove now this, and the diameter is bound below by the injectivity radius of any orbit, right? And so yeah, right. So this is the last slide. We have some questions for further research suggested by this work. So first question is, does there exist a universal lower bound for the diameter of quotients of simply connected compact symmetric spaces, depending only on the rank? So the case of rank 1, of course, is our result, right? I mean, yeah, because we did it for unit sphere, but for compact rank 1 symmetric spaces is the same thing, and the classical ones, and the Cayley plane is only one space, right? So it doesn't matter really. We don't need to worry about the Cayley projective planes. So right. So another question is, oh yeah, and the assumption about the rank is important. Otherwise, there are simple counterexamples. It must, you cannot drop these. Okay. Okay, another question is, okay, yeah. Well, of course, we can change the sign of the curvature, right? So consider quotients of a real hyperbolic space. And so, for instance, smooth quotients were hyperbolic manifolds or hyperbolic orbifolds. Is there universal lower bounds for the diameter of hyperbolic orbifolds? And the last question is, Right, remove the group action, just consider singular Riemann foliations. Does there exist a universal lower bound? This is not known, even for fixed n is not known, okay? But it is known for the known examples, right? The Clifford foliations, the composed foliations that Hadesky constructed, then it's okay, but not in general, yeah. Okay, so I'm going to stop here. Thank you very much.
Thank you, Claudio. Very interesting talk. Are there any questions?
Sorry, for the singular Riemannian foliation case, I mean, are there some particular cases or just absolutely nothing is known? I'm sorry, I think.
Well, for the known examples, right?
Of
You know,
singular Riemannian foliation.
then I think it's known, yeah. For the known examples, you know, these Clifford foliations and composed foliations that he constructs, take a homogeneous foliation and iterate with Clifford foliation. And I think for that, you have lower bounds. But otherwise, in general, I think it's not known, not even for fixed n. I think it's not known.
Okay.
Yeah, because we use very strongly the group action in our arguments. Very strongly, yeah.
Awesome.
And is there a hope to estimate this delta explicitly?
Oh, yeah, this is a good question. Yeah, for connected groups especially, right? Because of course there's Ben Green's result for finite groups. Yeah, I think it's a lot of work probably, but theoretically it could be done, I guess.
Because then you would get the asymptotic lower bound by Green's result, right? Yeah.
Sorry? No. I mean,
if you have the lower bound
for finite groups.
No. Sure. If you get it for the connected ones, then combining with the Green's results, maybe.
Combine, yeah, right. Yeah, theoretically, I think it would be possible, but it's really a lot of work. Yeah. Yeah. And of course, you don't want to get any estimate. You want to have some estimate in the range of the examples, more or less, right? Not very far away, right? In principle, I suppose.
Well, so, some estimate it will be fine.
Yeah, yeah. Yeah.
Claudio, I am not sure. Is it known if the extension of Ben Green's result holds for connected groups?
No, he really worked with finite groups. I mean, this is
I know, but
yeah. Okay. You mean going to pi over 2 as n go to infinity? Yeah, that's a good point. Yeah. No, I don't think so. It's not known. Yeah. Let me see examples, right? Yeah, for Coxter, maybe you can see something for in the case of Coxter groups, right? They're classified. And of course, yeah, these are finite groups. But I mean, you have like polar representations, right? Which you get the same orbit space. Yeah. Could be the same situation. I don't know. I didn't think about that.
Okay, thank you.
Any further questions for Claudio? Well, if it's not the case, then let's thank the speaker again for a nice talk.
Yes. Let me see how to.